At t equals 0, particle R, the red particle, is at the point minus 300, 0, and particle B, the blue particle, is at the point 0, 200. R and B have constant velocities 60I and minus 60J respectively. Find the velocity of B relative to R. So here we have the velocities of the particles relative to the fixed axes. We could also call these the velocities, the absolute velocities of the particles. We're interested in the relative velocity of B to particle R. So we imagine an axis moving with particle R. This axis moves with velocity 60I relative to the fixed axis. In the last video, we saw that to calculate VBR, we must calculate VB minus VR. We get minus 60J minus 60I. However, we normally write the I term first. Here is a picture of VBR. So from the point of view of the moving axes, B appears to move in this direction, whereas from the point of view of the fixed axes, B appears to move with velocity minus 60J. VBR has components minus 60I minus 60J. You can see an applet for this motion here. The fixed axes are not shown in the applet, but the red particle is 300 units from the origin. The blue particle is 200 units above the origin. Also shown here is the distance between the particles. VR, the velocity of the red particle, is 60I. VB, the velocity of the blue particle, is minus 60J. So in this animation we are going to see the absolute velocities of the particles. We can also select motion relative to the red dot. So we're going to look at VBR, the velocity of the blue particle relative to the red particle. So this is the vector minus 60I minus 60J. So we will just see the blue particle moving. So our moving axis is attached to the red particle. So we're just looking at the motion of the blue particle. To get VRB, the velocity of the red particle relative to the blue particle, we just reverse the direction of VBR. So we just change the sign of vector VBR. So minus 60I minus 60J becomes plus 60I plus 60J. So if we have an observer moving with particle B, that observer will see the red particle moving with this velocity, 60I plus 60J. We can see that in the applet. If we select motion relative to blue dot, we can see VBR has reversed direction. So now we have VRB, which is plus 60I plus 60J. So we're looking at the motion of the red dot as seen by the blue dot. The next thing we want to get is the speed of B relative to R. That's written VBR without an arrow. So the speed is just the magnitude of vector VBR. So we want the magnitude of minus 60I minus 60J. So this will tell us how fast the blue particle appears to move from the point of view of the red particle. So we're just getting the magnitude of this vector here. Well, that's straightforward. That's just Pythagoras. We just sum the squares of the components and get the square root. For this we get 84.85. Now, I haven't specified units in this question. I only stated what the velocities of R and B were without saying what the units are. So I'll just leave it as a unitless quantity. Actually, I think I will use units here. Let's make the distance of B above the origin 200 meters. So all the units are in meters. So the unit of distance here is meters. And let's say the unit of time is seconds. So the speed of B relative to r is 84.85 meters per second. You can see that it's greater than the absolute speed of B. The absolute speed of B, or the speed of B relative to the fixed axis, is 60. The magnitude of VB is 60. Find the shortest distance between the particles. Now we're going to use one of the relative velocity vectors to do that. First of all, we're going to look at the applet. Here we're going to look at VBR, the velocity of the blue particle relative to the red particle. So I'm going to start this applet, and initially the distance between the particles is 360.5, so we see that distance reducing. If we stop at about here, we see that the shortest distance between the particles, that is the perpendicular distance of the red particle to the trajectory of the blue particle, is about 70.9. As a matter of fact, if we play around with this applet, we will see that it's about 70.7. So to find this shortest distance, we need to consider the trajectory of the blue particle as seen by the red particle. So I'm trying to show it here in this diagram. Here's the trajectory of the blue particle as seen by the red particle. And when the blue particle is here, or well about here, then it's closest to the red particle. Remember, this trajectory has no meaning for the fixed axes. This is the trajectory for the moving axes. This is what it looks like. So at t equals 0, when the blue particle starts here, the coordinates are not 0, 200 for the moving axes. You can see that the coordinates are plus 300, plus 200. This point is 200 meters to the right of the moving axis, and 300 meters to the right and 200 meters above the moving axis. So I'll write the coordinates for the moving axes in yellow. So we have 300, 200 for the position of particle B at t equals 0. The first method I will use to find this distance d between the particles is to get the equation of the trajectory relative to the moving axis, of course, and then find this distance using coordinate geometry. Basically, we're using a formula for getting the shortest distance of a point to a line, where the point is the origin of the moving axis. So the point will be 0, 0. Now we need the equation of this line. Well, we have a point on the line. It's 300, 200, referring to the moving axis. So we now need the slope of the line. Well, we can get the slope from this vector here. We know that the components of this vector are minus 60i minus 60j. This is minus 60i, this is minus 60j, so this distance is 60, and this distance is 60. So the slope of the line is 60 over 60, which is 1. We could also see it, if we pick, say, this point here and this point here. The vertical distance between the points is 60, and the horizontal distance between the points is 60. We get that from the ij components of vector VBR. So we divide the rise by the run. 60 divided by 60 is 1. This line is positive slope. So now we have the slope and the point on the line. It's this point here. It's 300, 200 from this axis. So we can now write down the formula for the equation of a line. So x1, y1 is 300, 200. So we have y minus 200 equals m, which is 1, times x minus x1, which is 300. Simplifying this equation, we get y equals x minus 100. Now, From coordinate geometry of the line, the shortest distance of the point x1, y1 to the line ax plus by plus c equals 0 is ax1 plus by1 plus c divided by the square root of a squared plus b squared. Now, if you haven't seen this before, I will be doing this problem using another method. But anyway, I'll just run through this. We have to get our line in this form here. So, as you can see, it's not in the correct form for this formula. Now, we have the line in the correct form. It's in the form ax plus by plus c equals 0. So a, the coefficient of x is 1, b, the coefficient of y is minus 1, and c, the constant term, is minus 100. So we plug those values for a, b, and c into this. So a is 1. Now x1 is the x value of the point whose distance we're getting to the line. And, well, it's this point here, which is coordinate 0, 0 in the moving axis. Then we have b. Well, b is the coefficient of y, which is minus 1, times y1, that's the y value of the point, which is 0. Then c is the constant term in the line, which is minus 100. By the way, this c here is not the same c that we normally have when we have a line in the form y equals mx plus c. Actually, this should be plus 100. I'm sorry, it is actually minus 100. Okay, we divide this by the square root of a squared plus b squared, where a is 1 and b is minus 1. Well, minus 1 squared is the same as plus 1 squared. So we want the magnitude of minus 100 divided by the square root of 2. So these vertical lines means we're getting the magnitude of this quantity. The magnitude of any quantity is positive. So we just make this positive. To 2 decimal places we get 70.71 meters. So that's what we saw in the animation. Let's just run this again. Here is the vector VBR. We can see the trajectory of the blue particle, and the shortest distance, if we rewind it to 1 decimal place, is actually 70.7. So that's the distance I'm calling d in this diagram. The second method for doing this problem involves some basic trigonometry. We know that VBR, this vector here, is minus 60i minus 60j. So I'm just reproducing the trajectory of B as seen from the moving axes here. We're interested in this distance d over here, the shortest distance between the particles. So we will have a right angle here. We also have a right angle up here, of course, the angle between the fixed axes. We know that this distance here is 200. So we need that fact. Now we also need to find this angle here. Now we can find this angle here because we know what this vector is. If we look at the components of this vector, this distance here is 60, and the distance across here is 60. So I'm only looking at distances here. I'm forgetting about the signs of these quantities. In the right angle triangle that I've drawn here, where the vector VBR is the hypotenuse, the tan of this angle A is opposite over adjacent. That's 60 divided by 60, which is 1. Inverse tan of 1 is 45 degrees. So now we've found A. Now we know the distance of R to the origin of the fixed axis at time t equals 0 is 300 meters. R starts here, this position, minus 300. So we have this distance. Now we can also get this distance along here. Because we have a right angle triangle, we have an angle 45 degrees and we have a side. So we can use some basic trigonometry to get this side here. We can see that the tan of 45 is opposite over adjacent. So if I call this x for now, we can see that the tan of 45 degrees is x divided by 200. The side opposite 45 is x, the side adjacent is 200. So we see that x equals 200 tan 45. Now the tan of 45 is actually 1, so we have 200 times 1, which is 200. Now you might also have got this using the fact that if this angle is 45 degrees, then this angle down here must also be 45 degrees, because the three angles add up to 180. But if two angles are the same, we have an isosceles triangle, which means that these two sides are the same. So if this is 200, this distance x must be 200. So since this is 200, then the distance from here to here must be 100. And also we have a pair of opposite angles. If this angle is 45, then this angle in here must also be 45. Now looking at this small right angle, sine 45 is opposite over hypotenuse in this small right angle triangle. So to find d, we multiply the hypotenuse 100 by the sine of 45. So sine of 45 is 1 over root 2. So we get 100 times 1 over root 2, or 100 divided by root 2, which we saw earlier is 70.71 meters to 2 decimal places. Find how long it takes the particles to achieve their distance of closest approach d. So we want to find out how long it takes particle b to go from here to here, as seen from R. The first thing we're going to do is get the distance of this point to this point here. Now one way to find this distance is to get the distance of R to B at t equals 0. So get the distance between the particles in their initial positions. So we look at this right angle triangle here, and we can use Pythagoras to find out this distance. So we have to calculate this quantity using these two sides of the right angle triangle. We get 360.6. Now this is the distance that we want. We can see that this distance is part of this other right angle triangle, so we just use Pythagoras. This distance here is the square root of the hypotenuse, which is 360.6 squared, minus this short side here squared. We get 353.6 meters. Now we know that the speed of B relative to R is just the magnitude of this vector here. So we're dealing with particle B moving with a constant speed. Well, as seen from R, it appears to move with a constant speed along its trajectory. So we need to get the magnitude of its velocity. That's something we did earlier actually. So let's do that again. We need to get VBR. That's just the speed now. So the magnitude of this vector is got by squaring the components. Well, just calculate this. We don't have to worry about the minus signs when we're squaring. So now that we have the constant speed and we have the distance, we can find the time taken for B to go from here to here. Since we're dealing with constant speed, we can use the formula speed is distance traveled divided by time taken. And we can rearrange this to get the time taken. We just interchange speed and time. So the distance is 353.6 meters and the time is 84.85 meters per second. The meters cancel out and we're dividing by s underneath, so that's equivalent to multiplying everything by s. So the units will come out to be seconds. We get 4.17 seconds. A similar type of question that we could ask is, for how long are the particles within a distance of 75 meters of each other? Here is the picture. This line here is part of the trajectory of particle B as seen from particle R, which is here. So as long as particle B is along this part of the trajectory, then its distance from R is less than or equal to 75 meters. Now we have an isosceles triangle here. The perpendicular height of this isosceles triangle is the shortest distance between the two particles, the shortest distance that they achieve, which is 70.71. The perpendicular height of an isosceles triangle will bisect this base into two equal parts. So the first thing we will do is get the length of the part of the trajectory for which particle B is within a distance of 75 meters from particle R. So let's get this part. Let's just use Pythagoras. We have a right angle triangle. So this distance here is the square root of the hypotenuse squared minus 70.71 squared. To two decimal places, this value is actually 25.00, so that's very convenient. This is 25, I didn't expect that, and this distance here is 25 as well. So this distance here is 50. So now, just like before, we know the speed of B relative to R is 84.85. This time the distance is 50 meters. Time is distance over speed. We get 0.59 seconds.